Conservation of energy, conservation of momentum, and other conservation laws are the way nature reveals some of its underlying properties. This foundational feature in physics was unveiled by Emmy Noether in the form of a fundamental theorem that now bears her name. The crucial concept is symmetry. I want to show you what symmetry is, what it is not, and how Noether's theorem allows calculating conservation laws. Last time, I presented a step-by-step derivation of Hamilton's principle of stationary action and found how the difference between kinetic and potential energy naturally arises, giving us the celebrated Lagrangian. We derived the Euler-Lagrange equation and found that sometimes certain quantities like linear or angular momentum remain constant in time. They are conserved. But why do physicists care so much about conserved quantities? A simple answer is that knowing that a given quantity remains constant provides valuable information for solving equations at a later stage in time, thus allowing the prediction of the future state of a physical system. This is how we can predict how fast objects will move after a collision, how subatomic particles behave in colliders, and how to maneuver spacecraft in deep space. Early tabletop experiments in the 17th century revealed that some quantities appear to remain unchanged after the collision of two objects. Galileo, in his Dialogues, made mentions of the square of the speed of a falling object as a relevant property in 1638. This was followed by René Descartes' definition of quantity of motion and its conservation in 1644. Descartes' conservation of quantity of motion is not exactly our modern conservation of momentum because he defined it as the product of the mass of an object and its speed independent of direction. This idea was challenged during the 1650s by Christiaan Huygens, who derived the correct treatment of the collision of hard spheres. In a work that he only published almost 20 years later, he wrote, "The quantity of motion that two hard bodies have might change, but when the quantity of motion in the opposite direction has been subtracted, there remains always the same quantity of motion in the same direction." This sounds confusing, but in modern words, Huygens is proposing that Descartes' quantity of motion must replace speed by velocity, turning it from a scalar into a vector. The sum of the products obtained by multiplying the magnitude of each hard body by the square of its velocity is always the same before and after the collision. Today we recognize these two principles as the conservation of linear momentum and kinetic energy. Over a decade later, Gottfried Leibniz presented in 1686 ideas that appeared to contradict Descartes and proposed a new conserved quantity proportional to the square of the velocity that he called vis viva, Latin for living force, and similar to what we now call kinetic energy. The following year, Newton published his famous Principia, formally introducing the definition of linear momentum. The whole story is fascinating, and I had just scratched the surface here. In case you're interested, I will leave a link in the description to this great paper that goes into the details. Back to conservation laws. Over a century after the development of analytical mechanics, Einstein in Berlin was trying to properly understand what his own theory of general relativity implied for conservation of energy. In Göttingen, David Hilbert and Felix Klein were addressing the same problem but making little progress. In the summer of 1915, they invited a mathematician named Emmy Noether to join them. She had received her doctorate a few years before under Paul Gordon, a name that might bring some memories to those who have used the famous table of Clebsch-Gordon coefficients in quantum mechanics. For her doctorate, Noether became an expert on the calculation of so-called invariants, which Hilbert considered to be what they needed for solving the riddle of conservation of energy. Although Noether was not a physicist, not only she solved the problem, but she presented a theorem that was so general and fundamental that it is the basis for every single theory in modern physics. What Noether found was that conserved quantities in physics are just the consequence of continuous symmetries on the physical laws. This is how we get to one of the most essential concepts in physics: symmetry. Symmetry is at the heart of physics. Many people like to associate symmetry with beauty or elegance, but I find this to be subjective constructs. Personally, I find deviations from exact symmetry more interesting, and I like to think that the partial lack of symmetry is in many cases the reason for very rich phenomena in physics. But I am biased. This was in part the topic of my doctoral dissertation. In fact, I was quoting from my thesis. In case you're curious, I studied how possible deviations from the symmetry underlying special relativity, called Lorentz symmetry, would affect subatomic particles called neutrinos. I should maybe make a video about this in the future. In physics, symmetry refers to the invariance of a physical system under a particular transformation. This means that a transformation of the generalized coordinates leaves the system unchanged. Here we have to be careful. Unfortunately, most textbooks only glance over this very important point. To explain this better, let's consider a physical system represented by this yellow circle sitting on this one-dimensional coordinate system. We will apply a simple transformation called translation. In particular, we will transform x into a new coordinate x prime equal to x plus 1. A crucial point is that there are two ways to perform a transformation, referred to as passive and active transformations. In a passive transformation, we don't do anything to the system. We just relabel the coordinates of the configuration space. On the contrary, in an active transformation, we do not relabel the coordinates. Paraphrasing Lenny Susskind, an active transformation is an instruction to change the experiment. Wherever the physical system is, move it one unit to the right. Notice that the initial and final coordinates of the two types of transformation coincide. However, there is a huge difference. In the passive case, the physical system remains untouched. Only the labels used to describe it are transformed. Whereas in the active transformation, the system is moved to a new point. If we only focus on the initial and final coordinates of the object, we see that these two transformations are mathematically equivalent. However, from a physics point of view, they are not. Only one of these reveals the presence or absence of a symmetry. Before diving into the mathematical formalism for describing symmetries, I want to make sure that the conceptual aspects are clear. Given these two ways of performing a transformation, we can address the question: what is a symmetry in physics? The invariance under active transformations is what defines a symmetry. This is the transformation that matters when studying the physical laws of a system. This might be the most important take-home message of this video. Symmetry is the invariance of the equations of motion under the active transformation of a physical system. Passive transformations have nothing to do with the physics of the system under study. For this reason, the invariance under passive transformation is not related to a physical symmetry. In fact, a passive transformation is just a change on the observer rather than the physical system. We do this every time we take a picture in landscape mode and then in portrait mode. We do not transform the object that we are capturing. We just rotate the camera. And the laws of physics will look the same independent of the orientation of the camera. But here is the source of confusion. When there is a symmetry, passive and active transformation are equivalent. This is why many textbooks don't bother stressing their fundamental difference. However, when a symmetry is broken, active transformations become useless from an experimental point of view. But I will leave that for another video. Let's see another example. a rotation in 2 dimensions. We start with a system represented by this circle with an arrow pointing along the y-axis. This arrow could represent an internal property like the magnetic moment of a particle or a simpler vector like its velocity. Under a passive rotation, the components of both his position and vector change, but nothing has happened to the system. I am only showing you this for completeness, because as we know now, this transformation has nothing to do with symmetries. When we actively rotate the system, once again the components of both its position and vector change. If we perform an experiment and find that the system behaves just like before the transformation, we say that this system exhibits rotational symmetry. Let's now move from the conceptual to a more quantitative approach and see a few examples of physical systems invariant under particular transformations. We will only focus on infinitesimal transformations. Any finite transformation can be obtained by consecutively applying the infinitesimal transformation. Consider a free particle in 1 dimension, whose Lagrangian is just its kinetic energy. Its momentum is m times q dot, and from the Euler-Lagrange equation, we find that this momentum is constant. We say that p is conserved. Let's see how the Lagrangian of this system changes under an infinitesimal active translation of its coordinates, where epsilon is a small constant. We define the infinitesimal transformation delta q as the coordinates after and before the transformation. This is the new Lagrangian, but since q dot and q prime dot are identical, the new Lagrangian is equal to the original. In other words, delta L equals 0. As I will show you in a minute, the coordinate transformation and this invariance of the Lagrangian can be used to derive that p is conserved. Consider a system of 2 identical particles in 1 dimension under the action of a potential that depends on the distance between them. The momentum of each particle is m times q dot, and from the Euler-Lagrange equations, we find that the momentum of each particle is not constant. However, if we add them, we find that p1 plus p2 is conserved. Each momentum is no longer conserved, but their sum is. Let's see how the Lagrangian of this system changes under the simultaneous translation of the 2 particles. This is the new Lagrangian, and replacing the transformation, we find that we recover the original Lagrangian. Again, delta L equals 0. Let's use Cartesian coordinates to describe Kepler's problem, a particle in 2 dimensions moving under the influence of a central potential, meaning that this potential depends only on the distance to the origin. The 2 momenta are m times the speed in each direction, and from the Euler-Lagrange equations, we find this complicated time evolution of each momentum component. We do not get anywhere by adding them or subtracting them. However, if we multiply the first equation by y and the second equation by x and check the difference, we find a conserved quantity. Let's see how the Lagrangian of this system changes under an infinitesimal 2-dimensional rotation in the xy plane. This is the general way to rotate coordinates in 2 dimensions. But since we only care about infinitesimal rotations, we can approximate the sine and cosine function to leading order in epsilon in this way. This is the new Lagrangian, replacing the transformation and keeping only leading order terms in epsilon, we recover the original Lagrangian. Again, delta L equals 0. Let's consider a general system of particles and apply a time translation. This corresponds to studying the physical system at a given time and then a few moments later. Using the chain rule, we find that under this transformation, the coordinates q change by this amount. Note that there is no momentum conjugate for time. Thus, if anything is conserved, we do not know what it represents. Let's check how the Lagrangian changes. Plugging the new coordinates and only keeping leading order terms in epsilon, we find that the new Lagrangian is the old Lagrangian plus this extra term. Contrary to the previous examples, the Lagrangian is not invariant. I will show you that despite this, we can still find a conserved quantity. These examples and the way the Lagrangian changes under the corresponding transformations should give us a hint about how we can quantify the meaning of a symmetry in equations. I bring back the definition of symmetry and write the Euler-Lagrange equations for the old and new Lagrangian, before and after the transformation. Our goal now is to find the most general way of defining symmetry with equations. From the previous examples, we could define a symmetry as a transformation that leaves the Lagrangian unchanged. This indeed produces the same equations of motion, so it works. However, notice that the new Lagrangian could differ from the original by a constant, and we still get the same equations of motion. This means that an invariant Lagrangian is not the most general statement. In the previous video, I showed you how the Euler-Lagrange equations are derived from Hamilton's principle, so we could propose a more general definition of symmetry as a transformation that leaves the action unchanged. This would also work. However, what really matters to derive the equations of motion is not the action itself, but its variation, to satisfy the stationarity principle. Thus, this is the most general statement to define a symmetry. We want the variation of the action to be identical before and after the transformation. This means that the old and new action can differ by a constant that I call here epsilon a, just to explicitly factor out the infinitesimal variation epsilon. In terms of the Lagrangian, we get this. The constant a can be anything. In particular, we could write it as a general function g evaluated at the initial and final points. Now, using the fundamental theorem of calculus, we can take the function g inside the integral as a total time derivative, and comparing the integrands on each side, we get our result. Symmetry corresponds to a transformation in which the new and old Lagrangians differ at most by a total time derivative. This is a very important result, and it is the starting point of other fundamental and advanced topics like canonical transformations, action angle variables, and Hamilton-Jacobi theory. Writing these results using the infinitesimal variation of the coordinates and the Lagrangian, we get the following. Now let's put our definition of symmetry aside for a moment, and let's explore how the Lagrangian changes under a coordinate transformation. Using the chain rule, we get one term for the change in coordinates q and another for the corresponding change in speeds q dot. If we assume that the system evolves according to the principle of stationary action, we can make use of the Euler-Lagrange equations to replace the two partial derivatives of the Lagrangian to obtain an expression only in terms of derivatives of the coordinates and the conjugate momenta. Using the rule of the derivative of a product, we can reduce these two terms into a single one. Finally, replacing the general form of the coordinate transformation, we get this expression representing the change of the Lagrangian. Notice that now we have two ways of writing the change of the Lagrangian. Setting them equal and grouping terms on one side of the equation, we get this relation, which tells us that the combination inside the parenthesis is constant. This is a conserved quantity. Let's denote this general conserved quantity by q, which satisfies dq to dt equals 0. Collecting all our results, we get the following. For any general infinitesimal transformation of the coordinates, given by this relation on the top left, we call it a symmetry if the Lagrangian changes by at most a total time derivative. If this is the case, then we have demonstrated the existence of a conserved quantity given in general by the expression on the top right. This is Noether's theorem, or at least a simplified form of Noether's theorem. This is also the proof that conserved quantities, studied for centuries, are just the consequence of continuous symmetries of the system under study. I have not shown the full theorem, but Noether's theorem also works in the opposite direction. Given a conserved quantity, as long as the equation of motion can be obtained from an action principle, we can find the symmetry. I like to see Noether's theorem as a remarkable bridge between theory and experiment. It serves as a powerful guiding principle for building new theories, because if a new conserved quantity is measured in experiments, then we can directly find the symmetries that the theory must possess. Earlier in the video, I show you 4 examples of different physical systems, their corresponding conserved quantities, and transformation properties. Let's use Noether's theorem to construct the conservation laws. The first example was a free particle. We found that under this transformation, the Lagrangian remained invariant and the conserved quantity was the momentum p. From the transformation, we find that the function f equals 1 and g equals 0. Now using the expression above, we can construct q and find q equals p, in perfect agreement with the previous result. We conclude that linear momentum is conserved due to the invariance of the system under spatial translations. The second example was the system of 2 interacting particles. We found that under this transformation, the Lagrangian remained invariant, and the conserved quantity was the total momentum p1 plus p2. From the transformation, we find that the functions f1 and f2 are both equal to 1 and g equals 0. Q becomes this combination, which reduces to p1 plus p2, in perfect agreement with the previous result. We conclude that the total linear momentum is conserved due to the invariance of the system under spatial translations. The third example was Kepler's problem. We found that under this infinitesimal rotation, the Lagrangian remained invariant and the conserved quantity was this less trivial combination. From the transformation, we find the functions f1 and f2, and again g equals 0. Q becomes this combination, which reduces exactly to the conserved quantity, which is, up to a sign, the z coordinate of angular momentum. We conclude that the z component of angular momentum is conserved due to the invariance of the system under rotations in the xy plane. In the fourth example, we found that under this infinitesimal time translation, the coordinates and the Lagrangian change in this way, but we could not determine the meaning of the conserved quantity. From here, the function f is q dot and g is the whole Lagrangian. Q becomes this combination. If you have studied analytical mechanics, you will immediately recognize this expression. If you haven't, no worries. It is called the Hamiltonian of the system, and it deserves its own video. For a system of identical particles, we can replace the momentum p by mq dot, and after plugging the Lagrangian, we find that q is the total energy of the system. We conclude that the total energy is conserved due to the invariance of the system under time translations. Noether's theorem gives us a reason for conserved quantities in physics: symmetries. Here is a summary table relating some symmetries and their corresponding conserved quantities. If the location of the system under study is irrelevant, then linear momentum is conserved. If the interactions do not depend on the orientation in space, then angular momentum is conserved. And if the experimental results are the same today and tomorrow, then energy is conserved.